Correlation sensors are the most widespread and affordable type of sensors used for time-of-flight depth imaging. We propose to use this type of sensor, which can be found, for example, in the Microsoft Kinect, as a general-purpose difference imager. By modulating the sensor and the intensities of two different light sources, we utilize the architecture of time-of-flight pixels to subtract images of a scene under two different illumination conditions, even before A to D conversion. This enables us to implement various kinds of difference imaging scenarios. Here, for instance, we used polarized light to isolate direct and global components of light transport. Previously, to obtain only the direct component, two separate input images would have to be subtracted. Our system can do it in a single shot. Here we combine red and blue lighting and obtain a single shot imager that discriminates between reddish and bluish objects, with a positive and negative response respectively. The gray areas on the color chart don't produce any signal at all. Using the unique noise statistics of difference images, we can even estimate the red and blue channels separately, although we never observed them in isolated form. By introducing a spatial separation between the two light sources, we sense depth discontinuities from shadows in the scene. To the left, we see a video taken using our single-shot approach. To the right, we subtracted consecutive frames taken under alternating illumination. Note how the single-shot version is virtually free of alignment artifacts, while the two-shot version suffers from severe ghosting. Using a wider spacing between the light sources, we obtain information about surface orientation in a similar fashion to photometric stereo. Our camera can also be configured to sense spatial gradients. Here we use the birefringent crystal to create two copies of the image on the sensor. Then we subtracted one from the other in hardware. This highlights texture edges, while homogeneous areas produce on average zero signal. Finally, we make the system measure temporal gradients, or how much brighter or darker a pixel gets during the exposure interval. This results in a sort of bipolar motion blur, where the orientation of the motion vector can immediately be seen. In all of these examples, we made our camera system selectively sensitive for certain features in the scene. We anticipate that such configurable single-shot systems can benefit machine vision tasks and facilitate the analysis and compression of visual data in a wide range of potential applications.